So good morning. So far we have been discussing the static stability part of it, and from elevator required to stick force requirement, as well as there are gradients. For example, elevator per G, the d delta E by dN, then stick force per G, all these things we have derived. And at the end you realize that a lot of equations were there, but now once we understand the static part of it, we need to go for dynamic stability. And in that direction, we have already made a beginning. We talked about point mass model, that is how to write the equation of motion of a body in air, moving in air. And that was a very simple approximation. However, it is very useful. You will find in armaments, whenever they want to compute range of a projectile being fired, this point mass model works very fine for simple reason. Those shells like a Bofors shells or 105 mm artillery shell, when they fly at a almost zero angle of attack for most of the firing angles. So as it flies at zero angle of attack, so naturally the force which it experiences primarily is the drag. That too independent of angle of attack, it is CD naught. However, when you are talking about dynamic stability, we need to develop complete equation of motion of an airplane, and we will see from those equations, if I disturb the airplane, how the airplane is responding. And by studying their response or studying their tendencies, we will try to understand whether this aircraft is dynamically stable or not. So it is important that we develop complete equation of motion for an airplane in motion. And you understand that airplane can have 6 degrees of freedom. When I am talking about an airplane, I am talking about a rigid airplane. Nowadays, with high-tech materials coming, you will find that a lot of flexibilities in the material, or the wing in particular, is unavoidable, sometimes desirable. So I am not talking about those conditions. I am not talking about the airplane which is rigid, that is the distance between two particles of any part of the airplane, they remain fixed. They don't move relative to each other, right? So that's a rigid airplane, like a rigid body. So with this assumption, we will try to develop equation of motion for an airplane. If I draw an airplane, I have to set the axis system, and I am talking about an axis system x, y, z, which is body fixed. X, y, z is a body fixed. And located at center of gravity. This point is at the center of gravity. Now it depends on the purpose. How do I align this axis? There are many ways you can align this axis for many exclusive purposes. But here, to start in a simplistic manner, we are aligning this x-axis, let's say, on the fuselage reference line. This line of symmetry may not be guaranteed. If I put x-axis along the line of symmetry, then you will see some cross product of inertia, moment of inertia will vanish. But we are saying, okay, at this stage, the x-axis is in the line of fuselage reference line here. When I say it's a body fixed axis, please understand, this axis is fixed with the body, with the airplane. So if the airplane moves, the axis also moves, right? So if an airplane takes an angular motion like this, then the axis which was x, like it will also move with the airplane. It's a body fixed. If it is going like this, everything is moving the same way as the body or the airplane in question is moving. Right? That is why I am calling it body fixed axis system. Now let me define another axis system, which is earth fixed. This is closely I can say this is inertial frame. I will explain you what is. Let me write this, then I'll come back to this. For completion of this drawing, let me write this is an earth fixed and inertial frame of reference. I'll talk about it, don't worry. What is happening, you see? When I try to write the equation of motion, if I throw a body, so this will be acted upon by various forces, right? One is, of course, the gravity force. Another is, as it is moving relative to air, it will experience aerodynamic force. And if on the body, if you are putting an engine, then it will have propulsive force. That is, if I see forces, if I write forces acting on an airplane or aircraft in motion, one is, of course, aerodynamic force. Second is gravitational force, or because of force of gravity. And third is gravitational, and third is propulsive. This is strictly true for airplane. If it is a space vehicle, then you will have all those interplanetary forces that will come into the picture. We are not considering those things because those things are not significant as long as the airplane is flying within the atmosphere. An airplane can only fly within the atmosphere because we have a wing, and our airplane is aerodynamic in nature, that is forces, lift, drag, etc. They come out of a relative motion between the air and the airplane. That is important. So this, if I try to write a keyword, I will write relative motion, or I call it air relative. Please try to understand this a little more. You all know that if this airplane is moving in air, it will experience lift, it will experience drag because it is in motion and there is atmosphere here. But think of a situation, if this aircraft is grounded and it is towed like this. It is not moving with respect to ground. It is not moving with respect to ground. But if suddenly wind starts blowing, possible, it could be wind. It's coming towards the head, we call it headwind. If it comes from here, we call it tailwind. And this is called headwind. So you could see, if there is a headwind or tailwind, it will again experience some aerodynamic forces. Although this aircraft is not moving in air, it's stationary on the ground. That is obvious because we know this aerodynamic force or aerodynamic forces, they depend upon the relative motion, the air relative. Okay? So even if it is having zero velocity with respect to the ground, but with respect to the air, it has a velocity. So it will experience a force. So for aerodynamic forces, it is important we keep our focus on relative motion with respect to the atmosphere. Clear? Gravitational, you understand, is basically, we will assume here g to be constant because the height is not that large, so that we need to take care of variation of g. Okay. Propulsive, you know, it could be a jet engine, it could be a piston prop, IC engine. But then another thing you should understand, when I am talking about these forces, as far as stability is concerned, the gravitational force will always act through the center of mass, and we are evaluating the motion about center of mass like this. Okay? So that will not have effect in this angular motion as far as stability is concerned, because the moment, because of the gravitational force, about Cg will be 0. However, you will have components in terms of moment about Cg because of aerodynamic forces, because of propulsive forces, depending upon where it has been kept. This is, in general, we should immediately able to visualize when we close our eyes and think, okay, it's done. Once you identify the forces, the sources where this force will be available for the airplane to interact, we need to now write the equation of motion. And when we talk about equation of motion, you go back to your, again, 10th, 11th class, and you will remember that famous F equal to ma. That is, if we apply an external force F on mass m, then you know that F and acceleration are related like this, or I can interpret it like this. If I apply a force F on mass m, I know how much acceleration it will generate. What was the assumption here? This is valid as long as I am applying this in inertial frame. What is the meaning of inertial frame? That means this frame, that XYZ, wherefrom you are measuring, this frame should not have any acceleration. Clear? So no acceleration. Now you can understand, this is the airplane, and you know this is X. I write B for body, YB for body, ZB for body. Now I ask a question, is this XB, YB, ZB axis, XB, YB, ZB axis system or frame? This is axis, system or frame, same meaning. Is it inertial? Is it an inertial frame of reference? That means if I am measuring anything with respect to X, B, Y, B, Z, B, can I tell that it's an inertial frame? So what is the question? So we'll ask, does this frame have any acceleration? If it doesn't have any acceleration, then we say it is inertial frame. But check here, since there is a body fixed, the body is moving, body will have rotation, body will have acceleration, both angular as well as translatory. So definitely XB, YB, ZB is non-inertial. In fact, that is, you'll find textbook they write rotating frame. So there is a problem. If I want to write F equal to ma, F I know from there, and I want to find acceleration, then our relationship is F by m, but the problem is this is to be applied in inertial frame. And whatever forces you are measuring, whatever velocities you are measuring, whatever distance you are measuring, that should be measured with respect to inertial frame. But unfortunately, XB, YB, ZB are non-inertial. It is not inertial frame. So how to apply this under such condition? Question is clear? Okay. So now we look for, let us define some inertial frame. Unfortunately, see, the problem is our Earth itself is rotating. So if I am fixing an axis system on the Earth, it looks like, yes, it is fixed, but it is also rotating. So then that is also not inertial frame. So what do I do? For space vehicle, there could be a point, many points people will define at infinity, right? And that way they can manage these situations in a relative sense. But for Earth, there is a problem. My axis system is fixing on Earth. When an airplane is flying, I'm seeing from here, measuring everything with respect to the Earth. But there is a safe corridor of assumption where we can operate and handle this problem. What we will assume, for our airplane motion, the angular motion of the Earth can easily be neglected, because they are not very long duration things, right? Okay. So what is the assumption is made? Neglect Earth rotation. The moment you put this assumption, this becomes, for all our purpose, for aircraft performance, an inertial frame. That is why we have fixed x, y, z or z axis on Earth. That's why Earth fixed, this was body fixed, and this is we are treating as an inertial frame of reference. Okay. Once we have done that, now let us again revisit famous Newton's law of motion, F equal to ma. If I go a little step back, if I try to go back and introspect what is this equation representing, we know that from Newton's laws of motion that F is equal to rate of change of linear momentum. You know, m into v is linear momentum. How to define linear momentum? Immediately the answer comes, linear momentum is m into v. But I would like you to think in terms of little bit of more philosophical definition. When I say mv, I interpret this as quantity of motion contained in a body. Quantity of motion contained in a body. Like v is meter per second, right? M into v is, I will think like quantity of motion contained in a body. Now if I do a closer look, as far as Newton's laws of motion is concerned, this should be on the reference to inertial frame. That is, whatever derivative you are taking, that should be with respect to inertial frame. Now if I expand this, what do I get? I get m dv by dt plus v dm by dt. So most of the cases we are dealing, we'll assume this part to be 0. That is, there is no change in the mass during the operation, although we understand that fuel consumption will be there. But we'll assume that fuel consumption is neglected. And that is how we are writing m dot equal to 0. This is one. But what is important? Important is now F equal to m dv by dt, and this should be done in inertial frame. IF is inertial frame. That means you have assumed Earth fixed frame is an inertial frame, so you observe what is the direction it is going, what rate it is changing with respect to an axis fixed on the inertial frame on the Earth, not with respect to an axis system fixed on the aircraft, because aircraft is rotating frame, it's not an inertial frame. So that is the catch point, and that is the basis which will be used to develop equations of motion, right? And typically we say 6th degree of freedom equation of motion or equations of motion, and that is why 6 degrees of freedom. We say 6 degrees of freedom, that is degrees of freedom. Why 6 degrees? You are should be very clear about it, you know it. This is x, this is y, this is z. So 1 degree this motion along x, along y, along z, and the rotation motion along x, y, and z. So x, y, z, this motion, and one motion this, one motion this, one motion this. Right? So there are 6 degrees of freedom. So what is the meaning thereby? We will develop an equation of motion through which I should be able to solve a problem that if I give elevator deflection, aileron deflection, how this airplane is changing in free space. And that should be characterized, captured by this 6th simulation. Right? Okay? That is our aim. And what is the problem we got stuck? We got stuck that, yes, F equal to m dv by dt, but we need to do, in respect to inertial frame of reference, this derivative. However, if I am working with a body fixed axis system like this, body fixed axis is BFA, this is body, This is fixed. This is axis. The problem is, if I operate on respect to this axis system, this is not inertial frame of reference, so I won't be able to apply Newton's law correctly. Okay? In a similar fashion, you know this moment, and they are related like this. Rate of change of h. H is what? Any guess? What is h? Could you recall? H is angular momentum. So in your class 10th, you might have read, if you recall, that mvr, right? That will help you. If this is r, and this is the mass m, which is moving with the velocity v, then r cross mv is the angular momentum that we used to study in class 9th, 10th, or 11th. And one of my teachers told me, if you want to remember what is angular momentum, remember like this: it is the moment of the momentum. So moment of the linear momentum. This is linear momentum, mv. And you know, moment means force into distance, right? So you think in terms of moment of the linear momentum is angular momentum. This is my teacher used to tell me, and that's to help me. Just for your, keep it at the back of your mind. If you try to develop physical feel for angular momentum, think like this. This is the moment. Moment is a effect. Moment causes an effect for rotation, right? Which causes rotation. So this moment of linear momentum is angular momentum. And as F equal to m dv by dt, I can write moment equal to rate of change of angular momentum. These two equations are to be utilized for, one is I get acceleration from here, linear accelerations. I will get angular acceleration from here. So I can get linear position and angular position by integrating all these solutions, right? So this is the basis. Only problem is I need to work with inertial frame. Okay, so this, if I understand and keep back of our mind, we'll see how simple it is to develop 6 degrees of freedom equations of motion. Now see the conflict. When I want to find aerodynamic force, aerodynamic forces, what did we discuss? We discussed it depends upon the relative velocity. Okay? It doesn't depend upon the ground velocity. That is, the airplane, if it is moving like this, and this is the ground, which is for our case inertial frame, the aerodynamic force here will depend upon what is the relative airspeed with respect to the atmosphere, not with respect to the ground. As I give you an example, if the airplane is stationary on the ground, but suddenly wind starts blowing, it will experience aerodynamic forces. So for aircraft, if I want to calculate aerodynamic forces, these are air relative, That means I'll be more comfortable when I operate with XB, YB and ZB axis system, because this will be very useful to get me air relative speed along this axis, XB, YB, ZB, right? Because we have seen ground, with respect to ground, it really doesn't matter. It's all matter is what is the relative air speed. That means if the body is moving like this, the atmosphere is stationary, is moving like this. So you know relative air will be this way, that way, and depending upon the orientation. So it's the relative air speed relative to XB, YB, ZB axis. Speed, air relative speed with respect to the body. Body means XB, YB, ZB axis. But these are not inertial frame. So we cannot directly apply it. So what is the issue? How to solve it? That is the big question. Please come back. Mathematically, I want to find derivative dv by dt and dh by dt in inertial frame. But we are finding these forces, they depend upon the air relative speed. So that is more because of, it's easier to solve a problem in xb, yb, zb axis because it's a air relative speed. Thank you very much.